This is Lab 4, Faraday's Law. The purpose of this lab is to explore Faraday's law through collecting observational data of a magnet falling through a conductive tube of aluminum foil and modeling the magnet-tube interaction computationally and comparing both of the results. Some key concepts include Faraday's law, which relates the rate of the magnetic flux through a loop to the magnitude of the electromotive force. An additional term N represents the number of turns that are often included for coils of loop. We'll also use Beer-Savart law, which states that at any point the magnetic field dB to an element dl of current-carrying wire is given by mu naught over 4 pi times I dl sine theta over r squared. The magnetic force on the current-carrying wire is given by F equals ILB sine theta, where I is the current, L is the length of the straight conductor in a uniform magnetic field B, and theta is the angle between I and B. The force follows the right-hand rule with the thumb in the direction of I. So the procedure is to mark the north pole of the bar magnet, hold the tube vertically and position the magnet just above the top of the opening, record the magnet entering the top of the tube and leaving the bottom of the tube, find the time code where it enters and exits, and then calculating the time it took for the magnet to fall through the length of the tube. And we repeat this experiment 5 times and calculate the average time it takes for the magnet to fall through the tube. So first we create the tube of aluminum foil with the length of the tube m, the width of the foil m, the inner radius of the tube m, and the radius from the center to the outside surface. We then create the tube of aluminum foil as a series of rings stacked along the y-axis. The y-axis is perpendicular to the plane of each ring, and it passes through the center of the ring. Next, we create the magnetic field function and calculate d flux dt through each of the rings due to the falling magnet. Now we visualize the code by calculating the magnetic force from the tube on the magnet, computing d flux dt for the ring due to the falling magnet, coloring each ring according to the current, either counterclockwise or clockwise, calculating the magnetic force on the magnet, and finally plotting the graph of velocity versus time for the magnet as it drops. So here we can see the graph of the velocity versus time for the magnet passing through the aluminum foil. Our observed time was 1.06 seconds, and our experimental time given by the computational model is 1.334 seconds. And so now we can interpret the model. Which color corresponds to the clockwise current and the counterclockwise current? So the north end of the magnet is downward through the loop, and the magnetic field points out of the north end, and so there's a magnetic flux in the downward direction. And so the induced magnetic field will point opposite to the direction. So the induced current is in the counterclockwise direction. That means that the red will represent the clockwise current and blue will represent the counterclockwise current. What happens to the dynamics of the system when you flip the magnet? The direction of the current will be clockwise, but the velocity and the position will be unchanged. How does the total time of the tube in our real-world system and our computational model compare? And how would the computational model be made more accurate? So the total time is approximately the same. The observed was 1.06 seconds and the experimental was 1.334 seconds. The model does not take into account air resistance, which we could add to make it more accurate. We can also be more accurate by remeasuring the dipole moment and having a more accurate capture of the entry and exit times of the magnet. What does the shape of the velocity versus time graph tell you about the forces acting on the bar magnet? When the slope is negative, the net force on the magnet is only due to gravity. When the slope is 0, we know that the net force on the magnet is 0. So the force upward due to aluminum foil and downward due to gravity are equal and opposite. Therefore, the velocity is constant and we have no acceleration. So for our conclusion questions, what if the resistivity of the conductor were reduced as close as possible to 0? How would the dynamics of the falling magnet change? So if the resistivity was reduced to 0, we know that V is equal to IR, and so the induced current would be larger, or in this case, approach infinity. The magnet would take longer to fall due to that the magnetic force on the loop will decrease, and therefore by Newton's third law the upward force on the magnet will increase. What if holes or slots were cut into the tube, and how would this affect the ring currents? The ring currents would decrease due to the reduced number of rings. That would lead to a lower magnetic flux, and therefore the magnet would fall faster.